Imagine waking up and discovering that every memory, every scent, every sunset was rendered by a program, beautiful, convincing, and utterly synthetic. It sounds like science fiction, but the question, are we living in a simulation, is no longer just a late-night bar thought experiment. Physicists, computer scientists, and philosophers have begun treating it as a testable scientific hypothesis, one that pushes at the edges of information theory, quantum mechanics, and the very limits of computation. Today, we'll walk that razor. The history of the idea, the physical clues that make it plausible, and the experiments that might, if we're brave, try to catch the simulator glitch red-handed.
So this isn't just pop philosophy?
Apparently not. People with lab time and smoky equations have actually taken this seriously. The cosmic glitch. Why the simulation question keeps coming back. People have doubted reality for millennia, from Plato's cave to Descartes' evil demon. But what turned the simulation idea scientific was a crisp probabilistic argument and our own technological trajectory. Philosopher Nick Bostrom reframed the issue. If post-human civilizations can run many ancestor simulations, then simulated observers could vastly outnumber original ones, making it statistically likely that we are simulated. That's not proof. It's a Bayesian door left ajar. The question went from witty conjecture to something worth debating at conferences.
So it's partly a numbers game?
Exactly. Bostrom turned metaphysics into a probability puzzle. Extinction versus restraint versus us being simulated. Our own tech progress makes the idea less fanciful. We already render realistic virtual worlds and train AIs. Extrapolate a few orders of magnitude, and full history simulations become thinkable. Combine that with odd features of physics, fine-tuning of constants, the Fermi paradox, and the strangeness of quantum mechanics. And the hypothesis refuses to vanish. It from bit. When physics speaks information. Some of the most influential voices in physics point toward information as fundamental. The late physicist John Wheeler coined the phrase, "it from bit," suggesting physical existence ultimately emerges from binary information. Yes, no questions. In that frame, particles and space-time are patterns of information. The universe computes correlations.
So reality could be an information structure?
Yes. If the universe is organized as information, a computational substrate becomes a natural language to describe it. Relatedly, the holographic principle, pioneered in modern form by thinkers like Gerard 't Hooft and popularized in string theory contexts by Leonard Susskind, tells us a surprising fact. The information describing a volume of space could live on its boundary. That's literally a data on the surface picture, a hologram. If the universe's degrees of freedom scale like a two-dimensional surface, the idea that reality is encoded rather than continuous gains traction.
Holographic universe. That's not a metaphor?
It's a mathematically precise statement in certain models. Whether our cosmos exactly obeys it is an empirical question, but it frames reality as informational. Planck pixels, the possible resolution of spacetime. A hallmark of a simulated world would be discreteness, a smallest unit that plays the role of a pixel. Physics gives us candidates, Planck length and Planck time. Scales, approximately 1.6 times 10 to the power of minus 35 meters, where classical notions of space and time fail. If spacetime is fundamentally quantized, it begins to look like a grid with finite resolution. The kind of signature you'd expect from a substrate that stores and processes bits.
So Planck is our pixel size?
It's a natural scale where our current theories break down. Whether that equals a literal pixel remains unknown, but it's a motivated place to look for rendering limits. Researchers have built instruments to probe whether space shows subtle pixelation. For example, Fermilab's Fermilab holometer experiment searched for tiny correlated position noise that would betray a finite information bandwidth in space. The idea, if space has a finite information capacity, that might show up as measurable jitter in ultra-precise interferometers. So far, results have been mostly null or constraining. But the experiment illustrates how the simulation idea pushes to actual measurements. Quantum quirks, observation, entanglement, and computational economy. Quantum mechanics supplies the most philosophically dramatic clues. Why do quantum systems appear to collapse into definite outcomes only when measured? Why do entangled particles show instant correlations across distance? Some speculative readings interpret this as the universe rendering details on demand, saving computational work until a measurement forces a definite outcome. In that metaphor, measurement is like a screen refresh.
Are we saying the universe lazily renders only what's observed?
Some models flirt with that intuition. It's a seductive way to picture the measurement problem. The act of information extraction changes which degrees of freedom must be resolved. Entanglement's non-locality can also be read as a bookkeeping shortcut. The substrate enforces global constraints instead of local messaging, producing correlations that look instantaneous in our effective description. Again, not proof of simulation, but an alternate lens. Fine-tuning and the Fermi paradox, hints or hype. The universe's constants, gravitational constant, electron mass, cosmological constant, appear remarkably suitable for complex structure. Some see this fine-tuning as evidence of design. Others invoke anthropic selection. In a simulation frame, fine-tuning could reflect chosen parameters in a program. The Fermi paradox, where is everyone, also tightens the loop. One solution: advanced civilizations run ancestor simulations and we inhabit one. Another, computational or physical limits curtail civs, making us rare. Both possibilities fit into simulation-aware thinking, though both also have conventional astrophysical answers.
So these puzzles are suggestive but not decisive?
Precisely. They're suggestive clues that make the hypothesis worth testing, but they're far from smoking guns. What would a simulator leave behind? Observable constraints. If our universe were simulated, what signs might we find? Think like a forensic investigator. Discrete signals, evidence of space-time granularity, Planck scale effects, bandwidth limits, anomalies in ultra-high-energy cosmic rays, or small violations of continuous symmetries that reveal finite processing. Rendering artifacts, statistical patterns in physical constants, unexpected cutoffs, or correlation structures that look engineered. Information bounds. The holographic scaling of information is a real constraint. If we measure bounds consistent with a finite information budget, it supports the encoded universe picture. Experiments, interferometers, gamma-ray burst timing, cosmic ray spectra test these possibilities. Much of the work has yielded null results or constraints, but null results are informative. They rule out easy simulation signals and tighten what a simulator would have to look like.
So we design experiments to disprove the simulation?
Exactly. The smartest science treats the hypothesis as falsifiable. Look for signs that would be incompatible with brute force simulation tactics. A practical takeaway: why this matters beyond thought experiments. You might ask, why spend lab time on such an exotic hypothesis? 3 reasons. 1. It reframes existing physics in terms of information, a viewpoint that has driven real progress, quantum information, black hole entropy. 2. It generates concrete experiments. Asking new questions often yields unexpected insights, even if the original hypothesis fails. 3. It forces humility. If our reality is information-based, ethics, meaning, and ontology demand new thought. That's not mystical, it's responsible philosophy combined with empiricism.
So even if we're not simulated, the inquiry sharpens physics.
Yes, the path is as valuable as the destination. Information limits and the holographic clue. The holographic principle, an idea that emerged from black hole thermodynamics and string theory discussions, gives a striking, testable flavor to the conversation. The principle suggests that the maximum information contained in a region scales like its surface area, not its volume. That's a jaw-dropper. It implies the universe's information capacity might be fundamentally bounded in a way that resembles data storage constraints in computing. If true, that boundary-like encoding could be read as a hint that reality is ultimately informational, the sort of architecture a simulator could plausibly exploit. This principle emerged from deep theoretical work in black hole physics and has matured into a serious component of quantum gravity research.
So space may already be coded like a hard drive?
In a metaphorical sense, the holographic idea suggests the universe's bookkeeping is stranger and leaner than we once thought. The map and the territory. If the universe is a simulation, it would be the strangest of mirrors. The map, information, computation, and the territory, experienced reality, entwined. Whether we're code or not, the work of science presses forward, test hypotheses, tighten constraints, and refine our metaphors. And whether or not a cosmic programmer exists, grappling with this question sharpens our understanding of information, computation, and what it means to be conscious inside a law-bound universe.
So the hunt continues, armed with lasers, telescopes, and ethics.
Exactly. We don't need certainty to do good science. We need clever probes, honest reasoning, and the humility to follow the evidence wherever it leads. If the idea of reality as computation wakes your curiosity, subscribe to Science Unlocked. We'll keep chasing the empirical edges, from Planck scale searches to gamma ray constraints, and unpack the philosophical fallout.